I don't care. I'm done with hybrid and online streams. Too much tech, too hard. Okay, I have good news and bad news. The good news is that I'm actually here, and it's all entirely down to modern painkillers. And the bad news is that I got to bail at 11:30 because I got to go see a GP and find out what's wrong with my back. Otherwise, we've got an hour and a half, and I only really have two things to say. So what are the two things that I have to say? Thing number one is the exam is at some point in the future. You probably know when it is better than I do because I don't have to care about it anymore. It's been kicked up to exams unit. And as you all know, it's old school exam rather than new school exams. So you're back with sitting behind a desk with pen and paper and all the usual stuff, which hopefully is a better experience than the last couple of years of having to do these things at home with uploads and all that sort of stuff. There were some good lessons in that, but I don't know that's the way to do exams long term. Everyone happy there? Cool. We'll come back to the exam in a minute. The other thing that I want to mention is, and it's the same as last term, and those of you who are doing 2114 will be familiar with it as well. Yessie is doing a research project on teaching methods at second year in school, and actually I'm going to let her say the rest for this. Yeah, shoot. Actually, how about I throw you?
Thank you. So yeah, first of all, I'd like to say thank you, Adam. So hi, everyone. So you probably noticed that someone is always sitting back there, and it's Yessie, and I'm doing a PhD project in physics education. Like, I want to explore your perspective of the teaching methods used in the second year courses. So last term, I think you have done this survey in PHYS2111, and this term I'd like to hear back again from you for PHYS2113 and PHYS2114 courses. So you probably noticed that Adam has already posted an announcement and link. So I appreciate if you have done filling the survey, and thank you very much. And I also know that this is the most busiest time of the week, and I agree with you that maybe this is very exhaustive for you, but I will highly appreciate if you can also spare your time, like 5 minutes to 15 minutes, to also redo the survey, another survey in 2113 and 2114. And I believe it's around last week, Adams announced it. And it's different from my experience in that for my survey, you will be asked mainly about perspective on teaching methods. And please don't worry that it is very confidential. I will not tell Adam or anyone about your identity, as it is against ethics. So your identity is protected. And also you will give recommendation to school, and you will help for my personal project, for my PhD project. And I would very appreciate your help in that. And for that, you if you feel it seriously, you will be you can join the prize draw. As similar to the last term, there will be 10 vouchers, $20 course vouchers for 10 students, and the highest price is $100 for only one person. And if you complete the survey, there is this expression of interest form at the end of the survey for the focus group discussion. The focus group discussion will take place around the week of term 3. So I will not disturb or disrupt your study period. So I will contact you later if you're interested around the week 14. So please fill in the expression of interest as soon as possible, or you can directly send an email to me. So the focus group discussion will be set up like a safe and comfortable environment. And for that, we will serve you pizza and soft drinks for that. And if you have any question, please email me. I think Zofia has sent you email for that too. Okay. Thank you very much. Thank you, Adam.
Yeah, and as Jessie mentions, Jono's chucking in $100 for each of the two prizes. He's tempted to give them as either cash or core lithium shares this term. Okay. Right. So that's pretty much everything. I have nothing left to say, so I'm just open to questions. It's pretty much everything for today. We either run out of questions and everyone decides they want to go home, or we hit 11:30 and I go off and try and get someone to look at my back. Yeah.
Some people might have already seen I posted that to Discord. I was running some issues maybe with my partial derivatives.
Yeah.
So if we're taking the derivative example, like let's say Q1, and we're doing well, let's say like del Q1 dot.
Mm-hmm.
So the velocity. And what we're differentiating is like Q1 times Q1 dot.
Mm-hmm.
Is Q1 or like, are they functions of each other? Do we need to think about like a chain rule there for partial derivatives, or are they like independent and we can just drag one of them out the front?
That's a good question. It depends what they are. So what you're really saying is you're looking at doing something a little bit like okay. Oh, that's better. Why can't I write up there? Probably because I'm putting my hand on the board. Say, for example, something like this, right? Let me make it really clear and put one dot and only one dot there. I don't know why I don't know what's happened to this interface, but it's not as good as it used to be. In this case, it depends whether Q1 dot is a function of Q1 or not, right? So, I mean, the purest way of doing it would be to say, look, do it the chain rule anyway, no matter what. But in the case where Q1 dot's not a function of Q1 explicitly, you would find out that that extra term would vanish and you could just not take it.
So if we don't know how Q1 dot is a function of Q1, then there's nothing we can really do, right? We just have to leave it as
then yes, what you would do is you would carry a term over.
Yeah.
Like you would use the chain rule because you go, well, I don't know, so I'll cover off the case where it might be, and then hope later on something more specific pops out of the problem in such a way that you can clean up that term. Either you find out what that is or it knocks itself out. You see this happen quite a lot gradually across second year and third year physics, but we never talk about it very much. So sometimes we just do it. Sometimes we know that the term's not explicit, so we leave that term off. Sometimes we leave the term on, and then later on down the string, it wipes itself out. We just go, oh, you know, this thing doesn't matter, so we get rid of it. The classic case is where you're taking a time derivative, and then you have the total derivative with respect to time, a whole pile of chain rule terms in the middle, and then the function with respect to its own partial with respect to time. So something like this will be a total. Oops. Yeah, it's become really slow. X, Y, Z, T, for example. Probably seen something like this in mechanics. Then what you'll get is dl on dx, dx on dt, plus dl on dy, dy on dt, plus dl on dz, dz on dt, plus all your other terms that you got hanging in the middle, and then dl on dt. And you'll see this like everywhere from quantum mechanics through to electromagnetism, this sort of form. And then often we just dump this or dump a couple of terms in the middle here, and just dump them so quickly that people often don't spot that we've made them disappear, and then this generates a confusion that's there. But yeah, as a general rule, you would do chain rule all the way, and then some of those terms would drop to 0, but you sort of see that they drop to 0 in advance and just knock them out.
Somebody in the Discord said that the way you formulate Q1 and Q1 dot is that they are independent of each other, like the way that Lagrange can formalize and that.
In an ideal case, yes.
Can't guarantee.
Exactly. Mathematically, it doesn't strictly hold. It's not a rule of the setup for Lagrangian problems. But the smart way to set the problem up would be such that that's the case, yeah, because it makes your life easier. And then in that case, a lot of this comes down to smart problem setup. Yeah, yeah, yeah. Finding an example of that would take a little bit of work. I guess it'd be a matter of looking through and finding a subset of problems where you can choose different coordinates, for example, and then finding one where you set up a good set of coordinates where that problem goes away, and another one where you got a bad set of coordinates where they're entangled. Just trying to think of whether there's one off the top of my head. I mean, for example, it's why sometimes like these slidey wedge problems, you have the coordinate running down the slope. It's a wise choice of coordinates because you could choose, for example, to do X and Y or something like that. And then you might end up with problems like this. Yeah. Yep.
What circumstances where a Hamiltonian won't equal T plus B?
There's a few. The main one that turns up is that the constraint is not time dependent, or is not time independent. So there's a time dependence to your constraint. So this is why in the spinning hoop problem that we saw, you end up with them not being equal. It's because the constraint actually varies with it has a time varying component to it. Like it's not just a hoop that's stationary, it's a hoop that's actually rotating in a plane. Now, if you dig in and think about that problem a bit more, what you realize is that there's you're really dealing with a non-inertial reference frame there. Because you got rotation, there's an acceleration. Because there's an acceleration, you now got a non-inertial reference frame. Non-inertial reference frames never behave well for Hamiltonian problems. In the end, that comes down to the constraint not being time dependent, but sometimes when you see non-inertial reference frames, you're not necessarily thinking about constraints. So I keep that as a rule in my head where, if it's non-inertial, it's not going to behave itself. If the constraint has some time dependent, or the constraint is just not a fixed, simple constraint, I probably suspect that it's not going to be straightforward. They're the main ones. There can be a couple of other little quirky things that pop up in more complicated problems, but for the most part, for any problem that you're really going to deal with, that'll be it. I mean, the other way that you sometimes see it put in books is that the Hamiltonian has a time dependence to it, but that usually comes from a constraint that's time dependent or a non-inertial reference frame. So yeah, there are different ways of looking at the same thing. I'd see it the other way round, that for the most part, if the problem is really obviously simple, you can just know that it's going to add up. If it looks complicated, be suspicious. Yeah.
Differentiate with respect to time. Zero, you say it's conserved. What does that quantity mean? On the system?
It's basically saying that the total energy of the system is conserved. And so what you have is a fixed amount of energy that basically can move from potential energy of the system that you're looking at to kinetic energy of the system that you're looking at, and back and forth, right? And this is where the non-inertial reference frames and constraints get complicated, because you actually then like some of your energy can slip, depending on how you look at the system, some of your energy is actually hiding in the non-inertial reference frame when you look at the whole energy of the system. Yeah, I mean, let's say the hoop's not rotating, right? Then what we've got is a bead. The only thing in the system is the bead, because everything else is fixed. All right, they're all constants. You can make them go away. In the same way that in like the one thing you realize when you do Lagrangian method is that all your constants kind of vanish. All right, you only really worry about terms that are changing. The same happens for Hamilton's method because all you're doing is a change of variables. So the physics there should be the same. And so you consider your bead at the top. It's now got heaps of potential energy. Anywhere that it goes down here, it's converting that potential energy into kinetic energy, such that at the bottom, it's actually given up all its potential energy for kinetic energy, and then it'll do this, right? So anywhere in the system, you know that all you're doing is conversion of energy, and you've got a fixed amount of energy in that system. Now, if I start making the hoop spin, I'm not actually really doing anything to the bead itself. You know, for example, imagine the bead was sitting right at the top of the hoop and we spin the hoop. Well, I'm not giving any extra energy to the bead and my focus is on the bead, right? What I've done is I've actually put some extra energy into the system as a whole, but into the part that we assumed was constant before and making it change, right? And so it's now the total energy of the system is the energy of the bead, which was the thing that you're interested in, plus the energy that you've put into the hoop to make that hoop spin. But that the way you deal with that constraint is you remove the degree of freedom, which is the hoop spinning. And now that piece of energy has sort of become hidden. And that's why now the total energy no longer adds up to just the bead's potential energy and just the bead's kinetic energy, because as soon as these, if you think it from the spinning hoop problem, as soon as the bead drops down here, it's converted some of the potential energy it had at the top to some of the kinetic energy going in this direction. But now that it's slidden off the top, it's now subject to that motion in this direction. That energy has to come from somewhere, and it's not coming from the potential energy it recovered from here. It's coming from the fact that it's now subjected to the motion of the constraint, which you've hidden. And so this is the main reason ultimately why that idea of h equals t plus v breaks down whenever your constraint is not constant in time, because it takes energy to have the constraint change. That energy doesn't come from the same place that you'd normally think of it, and that's why it doesn't add up.
So it's the case where like the Hamilton kinetic was
Yeah, it depends on the system. It depends on the system as to how you interpret that extra contribution. For, you know, the bead on the spinning hoop, what you're now saying is, well, basically the difference is going to be the amount of energy it gains because it's now orbiting around the rotation axis. And that energy has to come from somewhere. It can't come from the potential energy that's coming down here, right? So it comes from somewhere else, which is from your constraint field, which is now why your energies don't add up, because you're kind of pulling magic energy from somewhere. You can imagine other systems where that might be different, like time-varying magnetic field, for example, something like that. You would probably interpret the effect that you would get of your Hamiltonian not adding up to the total energy of the thing that you're considering outside of its constraints in a different way. So you, in a lot of cases, you kind of need to look at how the problem's formulated to decide how to interpret what that is. It's just the one thing that's always the same is that when it doesn't add up, it comes about either as the energy to drive the non-inertial reference frame or the energy to drive the time variation in the constraint. And the interesting thing is that if you go through all the maths there and look at all the aspects of the energy, you'll notice that the bit that doesn't add up in that problem is omega dependent, which is the angular frequency for rotating the hoop. And yeah, it depends on how much of that is there.
Maybe it's a specific exam question.
Yep.
Often with Hamilton's equations, you end up with two first order.
Mhm.
One of them often just reduces down to something relatively meaningless.
Yep.
If the question says derive Hamilton's equations,
Mhm.
do we just derive that and show that, theta dot, I think the theta dot, and then the other equation, like just give an expression for P dot, or do we need to like actually find Q double dots like they did in the
It'll be pretty specific. So there's one or two cases there, right? Either you want to see both, and the question will tell you that it wants to see both, or you kind of just come into it knowing, well, one of them is going to be redundant. So there's one that I'm interested in, go after the one that you're interested in.
And there's no point. Like, is there sometimes a point to finding out
The other one?
dots? It doesn't explicitly pop out of the equation with like dots.
I mean, if you're looking for the equation of motion, you probably do want to convert it back to a double dot, because even in the case where you're not using both of Hamilton's equations, you're still usually trying to compare it to a result from a Lagrangian, and a Lagrangian is always going to get you the acceleration, not the momentum. So it would depend on the context of the question, but given most of the time, I mean, if you sit back and look, you'll spot the patterns running through, right? Most of the time it's like, here's a Lagrangian problem, do it. Now here, get through the Hamiltonian problem, and you'll probably get this, you should get the same answer, right? It's set up so that you should get the same answer because in some ways it's just helping you along. You know where you're going to get to, you just got to get to that. In that case, yes, it's very worthwhile converting it back so that you know that it hooks up. Given enough time in an exam, I would do the second equation for redundancy. But if you're tight on time and it's not explicitly asking for it, I wouldn't bother with it. It's like anything in life, you got to do a very quick cost benefit analysis. Is it worth the cost? If you're an hour and a half into the exam and you've finished, the cost is nothing and the benefit is probably small, but what else are you going to do? If you got 5 minutes left and some other question that's worth more marks to do, what's the cost is huge and the benefits are small. So yep.
Like, I don't really understand this.
It's not very important, so I'm tempted to not go over them. Just because I don't want to lead people to the conclusion that they are actually important in the context of this course specifically. Hey. I know how to do it. Yeah. I'm not sure. Yeah. Okay. Is it not going through? Okay. 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 Yeah. Cool. Thanks. Yeah, Poisson brackets. In a context of a mechanics course, do I really care too much? The main reason why I wanted to get to Poisson brackets in the end is that you see their analog in quantum mechanics, as commutator brackets. And a lot of what I'm doing when I do that is just hooking subjects into each other. If I could control the way that physics was taught, you wouldn't see quantum mechanics until after you've done a proper classical mechanics course. Because then quantum mechanics, part of the mysticism crap around quantum mechanics comes from the fact that a lot of people see it before they see mechanics courses these days. And it's easy to believe that somehow quantum mechanics evolved as its own subject, that, you know, suddenly someone was sitting around in a room and had some crazy inspiration. I mean, these inspiration stories are ridiculous. That you've got the whole, you know, Newton sitting under a tree, an apple falls on his head, and all of a sudden he decides, you know, oh, here's this theory of gravity. I've been reading this interesting Stan, which is about travel book about Central Asia, and in one of the countries there, they all these dictatorships remind me of universities, but in one of them they have this mythological story where someone was sitting under a tree and something fell out of the tree, and they had some big inspired moment too that goes back further in history than Newton, and so physics is full of these things, and they make you think that, you know, great ideas happen as an island unto themselves, which is absolutely untrue. And I think that's the main reason why I want to get to Poisson brackets in here, is for no other reason than you see start to see the analogs show up between classical and quantum mechanics. And if you've done like heaps of mechanics before you do quantum mechanics, and you come down quantum mechanics in the right direction for it, all you see is it's just an extension of it's basically just applying, not knowing precisely what the position of the particle is to your normal approach to doing mechanics. So I wouldn't worry too much about Poisson brackets. They're mostly there for your ongoing education rather than as something I want you to demonstrate an ability to deal with. Don't ignore those sorts of things, though. They're useful to know.
Are the images in the correspondence of this exam, or should we focus on just doing the tutorial questions?
Very good question. And I wish more people asked themselves exactly this question. My basic answer to it is that the relevance scales with time. So the closer it is, the more likely it is to be the case. There's a few reasons for that. One is that a subject will evolve as a function of time. So for example, I think someone asked whether I taught the course this morning on the Discord in 2019. I didn't, I wasn't even here. The years before that, I never taught it. So the first time I taught this course was 2020. So whoever was, all the exams before 2020, you're basically seeing somebody else's version of the course, somebody else's idea of what exam questions should be. My personal opinion is they're probably a little hard than back then than they should be, but they are what they are. Then you come into 2020. Well, 2020 is a funny year because if you go back and have a look in the history, the course was slightly different. It was a whole pile of, like, it was because it was the first year I taught the course. Basically, I just came in and took what they had last year and taught that. So I had all sorts of stuff with rotation and non-inertial reference frames and all that sort of stuff, which in an ideal world, we'd teach you all. I think it's fantastic stuff. But the problem was there was so much stuffed into, you know, your 3+ term length that it was just unmanageable. So a whole pile went overboard, and that was all the rotational stuff. So 2020, there's a whole question there that's actually just completely useless to you. And actually, I'd almost say both of them, because trying to think back, what was the questions? Huh? Yeah, that one will have rotation. That'll be rotational dynamics, right? Because there's a Coriolis force. Surprisingly enough, someone actually really got that answer on target. Like, it was spectacularly good. I should have offered a prize for the person who was closest to the right number. So that's obviously an irrelevant question, right? 2021, we're getting closer. 2022, probably fairly representative because you'll see it, the course just starts to stabilize. So I would say, look, if you're wanting to study, have a look at the most recent 1 or 2 exams. I usually don't go back into the deep past, even when I was a student. The homework problems are probably a better guide because what I've tried to do is choose past exam problems as the homework problems. So in that case, what I've done is probably gone, well, which are the ones that are more similar to the ones that I tend to give every year? So, I mean, they're probably more of your guide. The rest of the time I'd be spending on trying to get your head around making sure you've got all the concepts together and stuff like that. I had an emailed question from, and I might share it because it's actually useful. I had an emailed question about question 2 from last year's exam. Basically saying, look, you know, lots of parts of this are difficult. And the tricky thing is that question's actually deceptively simple because I'm not looking for very precise answers. I'm looking for physics person to do what physics people mostly do. And this is the weird, like you can fall into a very easy misconception as an undergraduate that what we tend to do is become more and more precise and do more and more elegant theories and more elegant algebra, when the reality is that often we actually go completely the opposite direction. Want to be less precise, want to know rough answers, want to know, you know, things to approximations and this sort of thing, because as things get more and more complex, your unknowns start to kill you a little bit. So I read lots of books. So I'm reading a book at the moment called Super Forecasting, which is about people who are good at forecasting systems. And the thing I really like about it, well, everyone loves having their own opinions reinforced, but the first chapter basically talks about, you know, looking at aspects of uncertainty and chaos theory in terms of prediction. And when I was a PhD student, I was doing work on quantum chaos, so that sort of hit me really strongly that uncertainty kills you after a while, and there's a limit to what you can predict because uncertainty always gets you in the end. Where was I going with that? So question 2 is really about trying to hit the things that matter and not the things, not be over precise with it. So really, question 2 can be answered from last year's exam in more or less 10 minutes at the most, and really is getting down to, do you understand how resonance works? Do people want me to hit it since it's fresh in my head? Because I imagine a lot of people, and I saw this last year, there are a lot of people who are like, oh, you know, started to try and write down really complicated equations from all the resonance stuff and never really went anywhere. And then you could see the people who had kind of turned up to the course, had taken all my hints about make sure you understand how resonance works and what's going on and all these other things. And then did get to the point of knowing that this was a really simple question. So what have I got? I've got a swing set. You got some floppy cable up the top. You got the mum swing, bub swing thing, right? It's me just trying to conjure up some ungoogleable situation that basically is asking you about physics, right? The old online exam days where I want to throw you for curve. I'd love to know how ChatGPT does with this question. Actually, I might do it. I might even make ChatGPT sit the exam while you're sitting the exam this time as well. Okay, so you need this thing at the top here to be floppy because otherwise you're not going to really couple the things into each other, right? If you go down to a park, pretty much every swing set has 2 swings on it. They've got the 2 legs pointing down. You've got a solid beam on the top, and you've got your 2 swings swinging backwards and forwards. Ideally, they have about the same length, so it would be the case where L equals L. And you can put two different masses on it, and quite often it's one big mass, one small mass. And you'll notice that there's almost no resonant behavior when you go down the park and do that, right? You either that, or you have to put two football players on there and make them flog the thing hard so that you can even get it to move a little bit and get a little bit of coupling from one to the other, right? But if you make it loose and floppy at the top so that, you know, you can couple vibrations from one side to the other via some, you know, again, in physics, sometimes we don't care about the details. We don't care about that coupling. We just need to know that they're coupled, right? And so you'll have done this in labs. You'll have done this in Oleg's part of the course. You know about coupled oscillators. So really this question is, can you pull everything apart that you've learned in this course about resonance and damped oscillators and coupled oscillators and those sorts of things and get down to, you know, some nugget of understanding that enables you to analyze the system? So I can't remember the first two parts of the question, but we get to see, and we start looking at concepts, right? So we've got, I think if I remember correctly, concept A, concept B. This one has L equals L on 2. This one has L equals L, and this one has L equals 2L, because that makes sense for how I think about it. And the question is, you know, you put mum on the mum swing. We're designing this as a thing for kids. Which is the best version to have, right? Depending on the age of the kid, right? Because like if it's a really young baby, you probably don't want to shake them too much. So you might want the coupling to be poor. And, you know, if it's your a future adrenaline junkie, you know, 7-year-old Travis Pastana, for example, then you probably want this thing to go completely insane and couple in as well as possible, right? What do you know? You know that this thing is basically just a pendulum. So I think when C, it's asking something like, what's the natural frequency or something like this for this system, right? You know, this thing's really just a pendulum at the end of the day, and the natural frequency for a pendulum is just square root of G on L. Yeah. And if we want to work out what the drive, so the important thing to think about here is that this is going to be your drive, and this is going to be your response. And some of you could even go, look, let's drill this a little bit further even. What we've really got is a drive response, because the mum on the swing is going to drive that swing into the pendulum and drive that behavior. Then that's going to couple through the chain at the top to a secondary response on the other side, right? So you could even consider it that way if you want, but let's just assume that that whole drive, you know, person driving this thing, we can just decouple into the motion of this swing on the right-hand side. Will couple via the floppy cable at the top to make the second one move around, right? And some of the conjuring up for this question was there's a classic lecture demo. Have a look for it online on YouTube. Basically what you do is you have a wire along the top, you have a pendulum on one side, and you have a whole pile of pendulums along this wire. And they're all different lengths except one that's the same length. You make this pendulum swing, and what you find is they all start to swing a little bit. They all swing at slightly different frequencies, and the one that gets the highest amplitude is the one that's got the same length. And the problem that I had when I gave this exam last year was I wanted to use that that demonstration as the foundation for the question, but I knew everyone would Google the demonstration and find out all the answers. So I had to basically be clandestine about my question and hide it, right? Okay, so you can consider omega big M to be your drive frequency, right? So it's going to be G on L. And so it's going to be the frequency that's going to drive. So this is going to be moving at omega big M, which is G on L. Everyone happy? You're going to have a response here, omega little m. And it's going to be G on L. And we've got three different concepts. So we could split this out into, say, omega A, omega B, and omega C. This one is going to be G on L on 2. This one is going to be G on L, and this one is going to be G on 2L. And if you clean up all the algebra on this, this one ends up being square root of 2 omega B. This one, sorry, omega M. No. Yes. This one ends up being omega M, and this one ends up being 1 on root 2 omega M. Everyone happy? So, and you'll all know this innately, right? If you've got a really short pendulum, it swings back and forth at a high frequency. If you've got a long pendulum, it swings back and forth at a long frequency, right? And you know this goes roughly the right way. The longer of them has the lower frequency, and so it's the slower of the pendulums, right? So just physically, this connects up. So that's C. Then D, what we're looking for is to, if I remember correctly, was to rank the order of the coupling, right? So obviously, omega B is going to be the strongest coupling, right? It's got the same frequency, and they will all, all the energy will go across quite easily. The thing to remember here is that if you draw a graph of the response, so let's call it an amplitude or response as a function of the frequency. Yep.
Sorry to jump back. Maybe it's my poor understanding of the question. But when I first kind of read this, I kind of assumed it was like a forced oscillator. But we're just assuming it's forcing it at the natural frequency.
It's a forced oscillator. And the forcing is coming from here. So we could call this force, right? It's going to have its own natural frequency, and it's going to run at that natural frequency, right? If you go down the park, like you can predict the frequency of your swing, right? Has anyone ever done this before? Like, just go down the park, take a tape measure with you, measure the length of the chain on the swing, and calculate what the resonant frequency for the swing should be, and then go and ride on the swing. You can sit on there on a stopwatch and time how many times it takes to swing 10 pendulums backwards and forwards, and you'll find that you get the right answer. It's very hard to drive it at anything other than its natural frequency. Give it a shot, see how you go. Like, you want it to swing at half that speed. It just never does it. Even if you, like, I'd almost... There was once this university that actually made their final physics exam for all their undergraduates to do the firewalk. And so you basically, at the end of the firewalk, you got your certificate. And it was really just, do you believe in the subject enough to actually, do this? Because it's going to be fine. It would be the same thing. Go down the park, tell me, is this someone swinging just gently on the swing? Is the frequency different to when they're swinging like mad? And a lot of people would say, oh, yeah, it must be a higher frequency when they're swinging like this rather than this because they're going faster. No, actually, just do the measurement. As you reduce the angle, it's a small difference. Like, there's a little bit of small angle correction that comes in for pendula, but basically the frequency is kind of fixed, and it's very well fixed by just square root of G over L. And so the response here, well, now this is where this problem gets interesting, because if the frequency for, how this is going to respond is going to look like this, for example. This point here will be omega big M. Omega B happens to sit at the same spot, which is why you get the really big response. And then omega A will sit off to one side, so it will be here. And omega C will sit off to one side, which will be here. And then really this is just about determining which one of these two is further away from the top. Now, some of you will go, well, hang on a second, this is not a linear curve, but what you can do at the top here is just take Taylor's approximation and say that this thing at the top basically goes as an inverse parabola, right? So whichever is going to be furthest away of these two is going to be the lowest coupling of the two, right? Because they're not enormously far away. So really, you can just go in here and go omega C minus omega A. So it's going to be root 2 omega M minus omega M. So this will be root 2 minus 1. And then, oh, sorry. What have I done here? This should be A and B. Sorry. Yeah, come on. It's very slow. This should be C. No, this is A minus B. Okay. And then this should be omega C minus omega B. And this would be 1 over root 2 omega M minus omega M, which will be 1 over root 2 minus 1. One of these ends up something like 0.4 something. One of these ends up 0.2 something from memory, from looking at it this morning. And so the one that's closer of the two will be the next in the series. And then the other one will be last. So if you want maximum coupling, you would make them the same length, so that the natural frequency of the response matches the forcing frequency. If you want the minimum response, you just choose A, right? So if you're a product designer, you might do, bub swing mild and bub swing extreme or something like that. Comes with a free can of Red Bull. Put that into a kid and see how extreme it gets. And then I think there was a question about phase as well, right? So now if you look at the phase here as a function of frequency, this thing has a really sharp step function in it at the resonant frequency. So this would be omega B or omega M over here. So this goes from 0, it's pi on 2 when you cross, and it's pi at the top. And so omega A would be out here, omega C would be out here, doesn't matter by how much. And so you know that omega B is in phase. Omega A will be ahead. Omega C is behind. And so if you look at the demo where you have this pendulum on one end and all the other pendula, you'll notice if you really go in and carefully map the phase, that the shorter pendulum is swinging in the opposite direction to the longer one. It's sort of, there's a phase shift in the whole system. And then the last part of it is, well, what happens if I get rid of the cable at the top and put it as a solid beam? Well, the whole thing goes away. Coupling breaks down. And it's just like a standard swing in a park, which is why they design them with a solid bar on the top. And they make that bar at the top as solid as possible, particularly so that it doesn't twist. And so the really common way to design them is that you have a beam, you have these two brackets that come out, and then it pivots around here. And the main reason you do that is because if you tie it onto the actual post, you get a torsional mode in there, and that couples the two together. You wanted to cut that out, which is why you hang off it if you're a swing designer. And so, yeah, that's it. And so there's no big chunks of algebra in here. There's no handling these big equations. As I sort of mentioned a bit earlier back in one of the problem solving workshops, this is an example of something that looks, when you first see it, the mathematics is intimidating and scary, and your job is to kind of distill it down to, well, what is it? How do I connect this to reality? How do I connect this to, how's the system going to behave? What's it going to do in various places? What do the aspects mean? I don't want to rob you. As I said, I didn't want to rob you of the opportunity of having to do that in a case where it's actually not that difficult a system and you can kind of tease it out. Because when you get to second year and third year and fourth year, well, when you get to third year and fourth year, these things, no one will hold your hand, and you really have to do them. Like, what the hell does this mean? What is this telling me? Why is it like this? How do I connect it to things that I understand? But this question, ultimately, the students who did it really, really well just did it almost, to to pick my favorite Oleg Sushkov style, just distill it down to the simplest possible brass tacks you can. What do I know about how this system works, and how do I simplify that and get that together? And this question's more or less like that. As soon as you start trying to delve into the deepness of the equations in this problem, you end up getting things that are so precise that they probably don't really matter. Because you don't know the nature of the coupling at the top, and you don't know all these other things, and you're never going to get much precision out of this. Yep.
Do you ask a question of this word length and theory because it was an online exam, or this could be a question typical of any in-person exam?
Typical of any in-person exam, because it's very easy, in my experience, including as an undergraduate myself, I passed exams as an undergraduate where I would say that I did not actually really understand the physics. And not because of any well, there's lots of intrinsic faults, but one of them is that the exam didn't test whether I understood the physics. The exam tested whether I could do some ugly string of algebra that we've been shown to do in the course. And I didn't have to actually understand the physics to pass the course. This is why I've become such a fan of oral exams, because you can very quickly tell whether someone actually understands the physics or whether they're just regurgitating algebra at you. And this is why I think the path to becoming good at physics is actually, you have to be good at the algebra and the maths, but you have to be good at building an intuition for what that actually means. Like, what's really going on here? How do I connect this to reality in some way? And that's why I love those kinds of questions. I can't make the whole exam that. Sometimes I've got to test your ability to do the other parts of the subject, like, you know, derive something accurately, solve a problem accurately, those sorts of things. But for me in an exam, there's never not going to be a question of, you know, explain to me how you understand such and such, because that's where, I mean, it's half the subject. Yeah.
I like the number of just like the number of generalized rules. How would you like to explain that?
Yeah, pretty much. The way I usually approach that problem is I come in, I look at I guess the best way to see it is, what's the minimum set of coordinates that I need to be able to describe all of the behavior of the system? So you start off coming in going, well, how many coordinates is this in? And then constraints will knock some of them out because it just removes the need for them. And that's generally your degrees of freedom. There can sometimes, in limited cases, be latitude on that. It depends on the case. Some problems there's degrees of freedom that you would have in the problem mathematically, but that don't really matter. Sometimes you actually want to keep an extra degree of freedom for some reason, depending on the problem. But as far as the simple problems go, no, that's as simple as it gets. How many generalized coordinates do I have? How many can I knock out with constraints? What's left? That's that simple. The tricky thing always comes with exams, and I think people tend to always overthink exams. And it's easy for me to say people tend to overthink exams because I no longer do exams. But one day when you're no longer doing exams, you'll think, oh, damn, I spent all my time overthinking my exams. I think you've got to see it from the perspective of what the objective of the task is, which is to work out whether you actually know the important parts of the subject. And sometimes there will be a trickier part of some part of a question in there, which is mostly about sorting out who really knows the subject from who knows the subject. But for the most part, a lot of them are fairly simple, and things like, you know, degrees of freedom and constraints are usually pretty simple. But during the course, you will sometimes see examples where they're not so straightforward, and that's because the real world is not an exam. in the real world, you'll deal with cases which are a little bit more complicated, and sometimes the rules don't really hold. I tend to not like exam questions where you've got things where, you know, it's unusual, the rules really don't hold or something like that. So yeah, but sometimes there will be questions where you'll be expected to have a bit more insight into things than you otherwise might. That's generally, that's the place where you get an edge when you're a physics undergraduate, right? You become good at understanding how to build intuition and have good concept for the system and still be able to do all the mathematics and all the usual things. But that's where you get your edge, is actually that ability to understand what's going on. And that's usually where the good HD level questions are pitching at, trying to find who has that, who doesn't have that. But, you know, I was an undergraduate too at one point, and that was the thing that I realized in second year. That's where I had to start working to get my edge on all the other students, was like, this is where, you know, if you sit down and you analyze all the exams and go, all right, well, what are the HD, you know, how do I get myself a HD in here? Where's the bits that I'm not getting the marks, and that, you know, in the future I can get the marks if I get better at that part of the subject. They're almost always, that's where they're coming from, particularly when you get up towards, you know, the higher years. Yeah. Yeah, Lagrange multipliers, I generally consider them unfair exam questions because they're just too damn long. Do they test anything? Do they test anything that I really care about? Again, like, think about it as a cost-benefit analysis. They carry a huge cost because they take a long time to do. And what's the benefit to me as an examiner in determining how much of the course you actually learned by sinking most of my time into a Lagrange multiplier question? Very little. And I guess this is the other thing you kind of got to see a little bit. And I can understand how when you come into university as an undergraduate, you don't see it, because when I first came in, I didn't see it either. That, you know, there's a person on the other side of this process who's got an objective, which is, I need to go through and work out whether these people are ready to go on to the higher years of the subject, and whenever I'm happy to sign off that they know the things that I taught them. And I've got 2 hours to do it. I'd love a day. You know, given an infinite amount of time, I'd drag you all in and sit you down for 3 hours and quiz you on every piece of the subject in front of a blackboard and see where you can do it and can't do it. But that's not scalable from a business sense. And so I've really got 2 hours on a written piece of paper, and I can invest it in crazy stuff, or I can invest it in sensible stuff. And if you look at the course and you look at the past exams and you look it all up, you can pretty much tell what kind of questions are going to be in there. I'm going to want to know, can you do a Lagrangian? I'm going to want to know, can you do a Hamiltonian? Because, you know, the rest of physics, you're not going to see many Lagrangians. You're going to see heaps of Hamiltonians. So, you know, it's going to be pretty obvious you need to know where they come from. Do you understand forced oscillators, or resonance and those sorts of things, because they turn up all over the subject as well. Lagrange multipliers, cost-benefit analysis, for me, I never bother with it. For the most part, because if you're going to get down to using Lagrange multipliers in any real problem, it's going to take you hours and hours and hours. Like, even the simple problems for it take hours and hours and hours, let alone the hard ones. Yeah.
You go over holonomic coordinates.
The easiest way to see that is just, is the dynamics of the system path dependent? So the classic example is you just take a ball and roll it along a surface. And if you know, say roll some distance here and roll to there, or you roll a bit further and then across and then around, where is the point on the ball? Then you realize it depends on what the path is. That is a non-holonomic problem. And a holonomic problem is one where it doesn't matter what path you take to get from A to B, everything still hangs the same.
So no.
Yeah. The only thing that you need to know about that is that holonomic problems are all the ones that you can deal with pretty easily. Non-holonomic problems become a horror show. And I would literally just say it comes down to that. If you spot a problem that's non-holonomic problem, you're in for trouble. If you've got one that's holonomic, it's probably solvable by some easy technique. There's not much more to it than that. I wouldn't even bother asking it. If you walked away not knowing that, do I really care? No. If you walked away not knowing that, you'll probably find out the hard way when one day you get a non-holonomic problem and you try to deal with it with a simple approach and find out that it descends into a quagmire. And I guarantee everyone has that. Number of times I've gone days into a problem and then gone, oh man, I wish I'd learned this properly as an undergraduate because I just realized that I did something very, very stupid. Yeah, it's life. Got to see it in the context of your whole career. You're doing one course. You can't do every problem that exists. Eventually, later on, you'll find out. You'll sometimes have to go back and relearn your undergraduate stuff. Yeah.
So in special relativity, I had a special relativity.
I don't know because that's Oleg's part of the exam. I'd say it's probably better to ask him that question, more for the reason that you're likely to get an unreliable answer that I can't guarantee to be correct. And he's doing a session this afternoon anyway, so hit him on that one. I'm sloppy as hell with special rel. It's the other thing that you'll realize really quickly, that all of the people who are lecturing you will know absolutely everything about the topics that they teach, and the topics they don't teach, they've probably forgotten. And they'll either try to bullshit you or they'll be honest and say that they've forgotten, which I prefer to just be honest and say I've forgotten all my special rel. I'd have to go and look at books and all the rest of it. I know what's important. I know basically how it works and that sort of thing. But when it comes down to actual problems, yeah, I'm as good as any of you are. Anyone got any other questions? Everyone seems happy to call it a day. I think you'll be fine. It's not that crazy an exam. My best advice is same as usual. Don't focus on going crazy, doing too many problems. Spend the time on just making sure you've got how the whole subject works clear in your head. You know, my advice to go down the park and play on a swing if you haven't already done it. The weather looks a bit shit today, but you've got a few days. Go down the park and play on a swing and think about how this all works. What am I seeing in this complex set of equations and graphs that they showed me in this course that I can take a simple experimental system and play with? It's, yeah, it should be a first year lab experiment.
Should we have a solid understanding of like phase space and state space and the differences with that?
I mean, there is only one difference, right? One you're plotting P's and Q's and one you're plotting Q dots and Q's. And now that you've finished the subject, you can kind of see the link. One of them connects into Lagrangian systems, the other connects into Hamiltonian systems. The main reason why I point that out again is one of those things that nobody ever talks about it. And then, I mean, I do this quite a lot in second year subjects. I'm bringing things back that I wish could be fixed from when I was an undergraduate. So no one ever discussed phase space and state space when I was an undergraduate in all the courses I did. And then I ended up, you know, starting to do a PhD in, you know, aspects of quantum chaos. So I had to go and learn chaotic dynamics in quite a lot of detail. And even there, the books didn't talk about difference between state space and phase space. And after a while, you realize that something's not connecting up. And after, you know, 2 days of tearing your hair out, you realize, oh shit, I wish someone had told me the difference between phase space and state space and done it right back when it made sense. So it's really just that. It's not much more to it than that. Trying to avoid you tearing your hair out for the same reasons I tore my hair out at one point. You can tear your hair out for some other reason. Yeah.
Did you teach any of the courses besides quantum classical?
No, not at the moment. I'm actually on sabbatical next year, so I'm teaching less next year than I'm this year. So this is my last year on classical. I will be back on quantum next year, and then I'll probably get slugged with a fat teaching load in 2025 to pay for it. Cool. All right, let's call it a day. I'm gonna go and take more painkillers. You won't need painkillers. You'll all be fine in the exam.